Hello everyone. Today we're going to prove the following statement. Let f be holomorphic on C with f of x plus y equals u of x plus I v of y, where u and v are real valued functions. And from this information we're trying to show that f of z takes the form az plus b, where a and b are both constants. So from here let's review what information we know. We know that f of z is some complex valued function, f of x plus iy, which takes the form u of x plus iv of y, where u of x is only a function of x and v of y is only a function of y. And we also know that f of z is holomorphic on the entire complex plane. Therefore, we know that the Cauchy-Riemann equations are satisfied on the entire complex plane. Once again, keep in mind that u of x is only a function of x and v of y is only a function of y. This is important when we're taking into consideration the Cauchy-Riemann equations. From here, we can look at one set of those equations, the partial of u with respect to y and the negative partial of u with respect to x. Since u is only a function of x and v is only a function of y, we know that both of these partial derivatives equal 0. So this equation doesn't really give us much information since it just tells us that 0 equals 0. So we'll look to the next one. We don't know u of x and v of y explicitly, so we can't explicitly calculate their partial derivatives, which makes things a little harder. But we do know that the Cauchy-Riemann equation is satisfied, so we know that the partial of u with respect to x is equal to the partial of u with respect to y. And another way of looking at this is moving the partial of v to the other side, so we get partial of u minus partial of v equals 0. From here we're going to use a little trick that I learned in physics actually when we were solving Schrodinger's equation. What happens if we pick some random complex number z to plug into the partial derivatives? Once again, we don't know the partial derivatives explicitly, so we don't know what numbers they'd come out to be. But we do know since u of x and v of y are real valued functions, we get real numbers out of them. So let's just say we plug in these derivatives, plug in x and y into these derivatives, and we get some numbers c1 and c2, where the partial of u with respect to x equals c1 and the partial of v with respect to y equals c2. So we get c1 minus c2 equals 0 from the Cauchy-Riemann equation, and we know this to be true. And for this specific complex number that we chose, since c1 minus c2 equals 0, we get that c1 equals c2. Now let's pick another number, w, where the real part of w equals the real part of z. So they're going to have the same x value, but they're going to have different imaginary parts. So the y value that we plug into the partial derivatives will be different. So we know u of x doesn't change since we're plugging in the same value for x. So once we get the partial of u with respect to x at w is equal to c1. But since we have a different value for y, since w has a different imaginary part, we get a different value when we plug this into the partial derivative with respect to y of v. And since we assume this to be a different number, since the imaginary parts are different, we'll call this c3. And since the Cauchy-Riemann equation is satisfied, we get that c1 minus c3 equals 0 once again. If you didn't catch it, we kind of just proved something important. We said both of these equations must be true since the Cauchy-Riemann equations are satisfied across the whole complex plane. We said that c1 minus c2 equals 0, and also that c1 minus c3 equals 0. The only way for this to be true is if c2 is equal to c3. Furthermore, since we know that both of these equations equal 0, we can just move C2 and C3 to the other side, so we get that C1 is equal to C2 and C2 is equal to C3, so all of these constants are the same number. This is important because we can extrapolate this to the entire complex plane for any complex number that we choose to plug in for f of z. We know that the partial derivatives will be the same, so we can say that these partial derivatives are constant across the entire complex plane. So we know the partial derivative of u with respect to x is equal to the partial derivative of v with respect to y for all complex numbers z. So we say that this equals some constant a, and we know that a is a real number since u and v are both real valued functions. And since the derivatives are constant, we know that this can only be the case if u of x and v or y are both linear functions, or else they won't have a constant derivative. So from here we can write general linear forms of u of x and v of y, where we say u of x equals ax plus b1 and v of y equals ay plus b2. We know that their slopes are the same since their derivatives are the same. They both equal a, but we had just assumed that they have different constants, b1 and b2. So from here we're going to plug these linear functions back into f of z. So we get f of z equals ax plus b1 plus I times ay plus b2. And then from here we can rearrange and factor out the a, so we get f of z equals a times x plus iy plus b1 plus I times b2. And we know that z equals x plus iy, so we say f of z equals az plus b. And we saw earlier that a was a real number and b is some complex constant. And this was the form that we were trying to reach from our initial assumptions.